I'm Hubert and this is Teach Me channel. So what are we going to learn about today? Today we are going to move away from maths a bit and we are going to do some biology. Namely, we are going to look at enzymes. We are going to look at what they are and why they are used in our body, and of course how they work. So let's start off talking about what they are to begin with. Enzymes are essentially catalysts. What does that mean? Catalyst is a substance or an enzyme that speeds up the reaction without getting used up in a process or without getting irreversibly changed. So enzymes speed up the reactions that go on in our bodies, or sometimes even outside our body when we use industrial enzymes. And they do that without getting used up. And another main feature of the enzymes is that they are specific. Enzymes are specific. And why is that important? Well, there is a lot of reactions going on in our body, and because enzymes are specific, we can speed up certain reactions in the body that we want to speed up. However, we can keep the other reactions in our body the same, essentially. So this is where the specificity of the enzyme comes useful, because if, say, we try to use a temperature to regulate our rates of reactions in our body, then we would not be able to pick and choose which reactions we want to increase. Of course, if we increase the temperature, then we are affecting all the reactions across the board. So the enzymes are specific. That's another important feature. And another important feature is that enzymes are large proteins, because that's what essentially they are. So why is this important? Because enzymes need to be able to mold. Essentially, we will cover this more in a minute, but they essentially need to mold themselves around the substrate, which is the substance they react with. They want to react, and they of course need to be large enough to do that. So now we will move on to why we use enzymes. So I'll put down here what. And now we will move on to why are we even bothering with using enzymes. So of course, as I already kind of mentioned, we are using them to control reactions in our body. So control reactions. There are so many things going on in our body. We have to do respirations in order to be able to get our energy. We need to be able to digest food. We need to be able to utilize the water that enters our system. We need to be able to synthesize certain nutrients. Perhaps even when we tan, we are making vitamin D, where of course enzymes are involved in most of these reactions. Most reactions that undergo in our body use enzymes, and most of those reactions also have to be tightly controlled, where we have to tightly control the generation of energy in our body. We have to control what nutrients we want from food, what nutrients we don't want from food, and enzymes are really, really helpful, and they really help us to achieve this aim. Because of their specificity, we have specific enzymes for specific single reactions that are involved in these large processes, and we can change the activity of those enzymes in various ways by using different compounds that may impact on the activity of the enzyme, or by changing conditions that this enzyme is trying to work in, as we will cover later. Another useful thing is that enzyme does not get used up in the reaction because it's a catalyst. So I'm going to put that down here. Does not get used up. So we can basically, in our body, we can make a lot of that enzyme, and then we can use it in a reaction throughout the whole reaction. We can use it throughout the whole thing without having to continuously create more and more of these enzymes. We can have them do that reaction, and then we can get rid of them or do whatever we want with them. And why don't they get used up? Because they are catalysts. They help the reaction to happen, but they don't actually get used up in the reaction, as we covered it. Now we know why we want to use enzymes, and we know what they are. So now we can move on to how the enzymes actually work. What do they do? So I'm going to put down here how. Okay, so enzyme, as we talked, is essentially a large protein, something like this. A large protein. Here is our enzyme. And here's the important part. Here we have active site. This is called active site. This place is where all the compounds that the enzyme is going to be reacting together need to go in. They all need to go into this site, and this is precisely where the reaction happens. Now, the important thing about the active site is that it has a very, very specific shape that corresponds to the compound that it is going to react. So, for example, if we have a compound like this, then it will not be able to react with the enzyme because the shape is wrong, and the shape simply will not physically fit into the active site, and therefore the enzyme cannot do anything about this. However, if we have a compound that is of the correct shape, something like this, then it can go enter the active site where the enzyme is able to react it. So the compound that is being reacted by the enzyme, the compound that actually does go into the enzyme, is called a substrate. I'm going to write it down right here. This is the very, very important names. Substrate and enzyme and active site. Those are all very important words when it comes to exams. Okay, so now we know that a substrate enters the enzyme, enters the active site of the enzyme where it is getting reacted. So this happens. We have the substrate enter this enzyme, and the reaction occurs. But some reaction occurs within the substrate, where it, for example, may get split, or it may be joined to something else. The enzyme may be using more than one substrate together. However, in this case, let's say that the enzyme splits it. So the enzyme splits it, and we are left with this. We are left with the enzyme, and we are left with the product. And here we still have our enzyme. And as you can see, the enzyme remained intact throughout the whole reaction. So So the enzyme acted as a catalyst. It sped up the whole process. The substrate did not have to take ages to split itself. It just quickly went into enzyme's active site, the enzyme split it, and now we are left with enzyme in its intact state. It's ready to take another one of these guys, and it's ready to carry on reacting these substrates, and we are left with the product, which the enzyme has made. So this is the basics of how it works. However, there are two important models as to how the enzyme works. First model is called lock and key model. Lock and key model. And this is exactly what I showed you here. Where the substrate enters the enzyme, the substrate has to have the exact same shape as the enzyme's active site. And in order for the reaction occur, this is the key to lock and key model. Exact fit of substrate. The substrate has to be of the exact shape, exact same shape as the active site. Now, this is the older model. However, recently we are accepting a new model. We are recently accepting a model called induced fit model. An induced fit model is essentially very similar. The basics are still there. However, the shape of the substrate is not exactly the same as the shape of active site. For example, we can have a little groove here like this in the active site, where substrate does not have that groove here. However, what happens is that when the substrate enters the enzyme, the active site of the enzyme, what happens is the active site slightly changes its shape. It slightly is able to change its shape to fit that substrate and to be able to react it. It is often called a conformational change, that the enzyme, that the active site of the enzyme undergoes conformational change to fit the substrate in order to be able to react it. So I will write it down for you here. Conformational change. So guys, this is how enzymes work. However, how fast they work and how well they work can be affected by different conditions that these enzymes are in. So today we will cover two conditions. We will talk about the temperature and we will talk about the pH, the acidity and the alkalinity of the environment that the enzyme is working in. So let's cover temperature first, shall we? So I'm going to put this down here. Temperature. Now, so temperature. The warmer it is, the hotter the environment is, the faster the little molecules, the substrate travels. So say if we have bunch of substrates like this, we have bunch of substrates and we have bunch of enzymes. So now if it's cold, these substrates tend to move around quite slowly. And there is a very little chance that one of these guys actually manages to enter the active site of the enzyme. So in this case, the reaction will go slowly. However, if it's hot, we have a similar situation where we have enzymes and we have a bunch of substrates. However, now, because it's hot, these guys, as well as the enzyme actually, these guys have more energy. They can travel faster and they can travel further. So they move around faster, they shake, they bump into enzymes, they bump into each other, so they're more likely to bump into enzyme. They're more likely to bump into enzyme's active site where they can actually be reacted. Therefore, the whole reaction goes much, much faster. However, so here it goes fast. However, we cannot overdo this. It goes up to a certain point. Because if we get way too hot, so say too hot, so we have the enzymes and we have the substrates. So these substrates are going super fast. They're going absolutely crazy. They're going really, really fast. However, the enzymes, because they are proteins, they are starting to get denatured. What that means? Denatured protein means a damaged protein, a protein that changes its shape, changes the bonding, and it breaks up the bonds, and it changes the arrangement of those bonds. So, because those proteins get denatured, as we talked, active site has to have a very specific shape. The active site changes shape. So, say active site becomes something like this. And now these guys, they cannot go in. So, therefore, the reaction, if all of the enzymes are denatured, the reaction stops. The enzymes cannot do anything here anymore. They're broken, essentially. Now I am going to show you on a graph. I'm going to show you what happens if we look at this temperature effect on a graph. So let's draw up a quick little graph here. So on the x-axis here we will have temperature. Whereas on the y-axis here, we'll have the rate of reaction, how fast it is happening. Rate. Okay. So, if we look at this, the graph will look something like this. So what do we have here? So, initially it's 0 degrees Celsius, it's cold, and the higher we go, the higher the temperature gets. It slowly increases the enzyme activity. So we can see a nice little slope here going up, so the rate increases as the temperature increases. Then the temperature wherever the enzyme's working fastest, we call this an optimum temperature. Optimum temperature. In our body, because our body is maintained at 37 degrees Celsius, this temperature is most likely in most enzymes, not all of them, but in most enzymes, it is going to be 37 degrees Celsius. And then here we're starting to see the enzyme denature, so the rate starts dropping rapidly because the enzymes are just getting broken and they are not able to catalyze the reaction, so the rate falls right down. It falls really, really steep. On a really steep slope, it falls down. And in most cases, 45 degrees Celsius is a temperature where most of enzymes will get denatured in a human body. So we're going to put down denatured here. Broken. So essentially this is a summary of how temperature affects the rate of reaction in terms of enzymes. So now we are going to move on to the pH of the surroundings that the enzymes are in, and how we will have a quick look at how this affects the rate of reaction. So I'm going to put down here pH. Okay, so the enzyme, again, the enzyme has its preferred pH because enzyme is a protein. Enzyme is a protein essentially. So we have our little enzyme. So again, it's a protein. And proteins are most stable, as in the proteins work best. The proteins work best and they are least likely to change their shape in a pH that is optimum for them, that they like. Each protein may have a slightly different pH, but most proteins in a human body, including enzymes, will work best at around pH of 7.4, around that area. So optimum pH is roughly 7. Now what happens to that little enzyme if we go way off somewhere with a pH that's really wrong? Again, the proteins can get denatured. They can get denatured because if we have a pH that's very different, then that affects the ionic reactions. We don't need to know that at this point, but it affects various chemical reactions that may actually damage. It can damage the active site of the enzyme, so it can get damaged, and in a very similar way as previously, the enzyme cannot work properly in such a defective state. Okay, how would we make this look on a graph? So let's draw up a very, very similar graph. Here, however, we will have a pH, and here we will have rate. Okay, so in this case, maybe I'll get different color. In this case, the graph will look somewhat like this. So the slopes on both sides of the graph are relatively equal, not as drastically different as with the temperature graph. And here again we have optimum pH, which will be roughly 7 degrees Celsius. And at these points, they may vary for different enzymes. They may vary, but at these points, they denature. Now, short it down here, and the same for here. So at these points, this enzyme denatures, and it cannot work. So how is this different to the temperature graph? Well, as we can see, the slopes are a bit more equal here than they are in the temperature graph, where in temperature graph we had it slowly going up, and then once it gets past the optimum, it really starts to sharply drop. Okay, so for most enzymes in a human body, pH will be of around 7. However, there are some enzymes that work better in different pHs. For example, pepsin is one such enzyme. Pepsin is in our stomach, and because it is in our stomach, as you probably know, the stomach has lots of acids, and therefore it has to be able to work in very, very acidic conditions. So pepsin actually works best at around pH of 2 to 3. So it actually works best in lower pH, in much more acidic pH. Okay, so this is essentially it. So today we covered the basics of enzymes, how they work, what they are, and how do we use them. Thank you guys very much for watching. And if you want to stay up to date on daily videos on science, on sciences, on maths, as well as later on some biomedical sciences for university level studies, please press that subscribe button below. And if you like this video, please give me a thumbs up. And I can't wait to see you next time. Thank you.